I have to be honest, when I first saw the title LLaMA pop up in the feed for today's deep dive, my brain went straight to, the animal kingdom.
Right, yeah.
Or maybe like a new wool production startup or something. But then I saw the authors, Hugo Tuvran and the team at Meta AI, and I realized we definitely weren't pivoting to zoology.
No, definitely not. Though, I mean, the name is incredibly catchy. It actually stands for a large language model, Meta AI.
Right. And looking at the date this paper dropped, it really feels like a distinct before and after moment in the whole industry. Because up until Llama, the narrative in AI was almost, well, comically simple. If you want to win, you just build the absolute biggest, heaviest thing possible.
The whole bigger is better era.
Exactly. It was a total arms race. You had OpenAI, Google, DeepMind, and everyone was just bragging about parameter counts. 175 billion, 540 billion. You needed a warehouse-sized supercomputer just to turn the lights on. And then Meta drops this paper that basically says, actually, you're doing it all wrong.
It was a massively disruptive thesis, to say the least. I mean, the central claim of the paper is that you do not need massive proprietary data sets, and you certainly don't need inaccessible hardware to achieve state-of-the-art performance.
Yeah.
They argued that smaller models, if they're trained on way more data, could actually outperform the giants.
And that's exactly the hook for us today. We're going to completely unpack how a model that is 10 times smaller than GPT-3 actually managed to beat it on most benchmarks.
Yeah.
But more importantly, I think we need to talk about why they did it. Right. Because this wasn't just, a fun science experiment. It was a complete philosophical shift in how we even think about efficiency.
It really was. And to understand it, it really starts with challenging the laws of scaling that everyone had basically accepted as gospel at the time.
You're talking about the Kaplan laws, right?
Right.
From around 2020.
Right, exactly. Kaplan and his team established a scaling law that suggested model performance was heavily, almost entirely, dependent on the number of parameters. Essentially, the bigger the brain, the smarter the AI. So for like 2 years, everyone just kept adding layers, just making the models wider and deeper and heavier.
But then DeepMind came along with that Chinchilla paper in 2022 and sort of pumped the brakes a bit.
Exactly. The Chinchilla team looked at it and said, wait a minute. For a given budget of compute, which basically means for a set amount of money and electricity,
right,
you are much better off making the model smaller, but training it on way, way more data. They proved that most of these large models were actually severely undertrained.
Okay, so Chinchilla set this new standard, which they called compute optimal. But here's where I get a bit stuck when looking at this. If Chinchilla solved the equation, why did the LLaMA team feel the need to push it even further? Because looking at the stats in the paper, they went way beyond what Chinchilla even recommended.
That is the crucial insight of the entire LLaMA paper. See, Chinchilla focused on training optimality. They wanted to minimize the cost of creating the model in the first place. But the team at Meta, they looked at the whole life cycle of these things and realized that training is only a tiny, tiny fraction of the overall cost. The real cost is inference.
Inference meaning actually running the model, putting it to work out in the wild.
Exactly. Think of it like a business investment, right? Training the model is your capital expenditure. You buy the factory once.
Okay.
But inference is your operating expenditure. That's the cost of running the factory every single day for years. If you strictly follow Chinchilla, you get a model that is cheap to build, but it might still be pretty heavy and expensive to run millions of times a day.
So Meta essentially decided to, overpay up front.
Precisely. They took a 7 billion parameter model, which the Chinchilla laws say should really stop learning after about 200 billion tokens, and they just force-fed it 1 trillion tokens.
That is 5 times the recommended amount of data.
And the really fascinating thing is it just kept learning. The performance didn't plateau like people thought it would. By overtraining a smaller model, they created something that is incredibly cheap to run later on. It's like the difference between a gas-guzzling semi-truck and a highly efficient hybrid car. The truck might be easier to build for hauling one huge load, but the hybrid is what you want to drive every day for 1 million miles.
That shift from a training budget to an inference budget, it really feels like the exact moment AI became a viable product rather than just a really expensive research project.
Okay.
But let's actually look at what they are feeding this thing. You mentioned 1 trillion tokens. Usually, when big tech companies talk about their data, it's all this highly guarded, proprietary secret sauce.
And that is the other massive differentiator here. LLaMA stands for open. Well, it stands for Large Language Model Meta AI, but the philosophy is open. They explicitly state in the paper, we only use publicly available data.
Wait, so no private user messages, no hidden archives from Meta's servers.
Nothing, absolutely nothing that a determined researcher couldn't just go out and scrape themselves from the internet.
Okay, so let's audit the pantry then. What are the actual ingredients going into this?
So the base, making up about 67% of the training data, is Common Crawl. This is essentially a massive snapshot of the public web. They use data dumps from 2017 all the way to 2020.
But we know the raw web is, well, to put it mildly, it's a dumpster fire.
Yeah.
It's full of spam, navigational menus, SEO garbage, and error pages.
It absolutely is. So the real secret sauce here isn't the data itself, but the cleaning pipeline they built. They created a specialized classifier specifically to distinguish between high-quality text, like the kind of writing you would find referenced in a Wikipedia article, and the total garbage.
Oh.
They filtered out non-English text, they aggressively deduplicated everything, and they just stripped out all the low-quality content.
Okay, so they heavily scrubbed the raw web. What else is in the mix?
Next, you have C4, which is another pre-processed web data set. That makes up about 15%. But the really interesting additions are the specialized data sets. For instance, they included GitHub.
The public code repository.
Yes. About 4.5% of the entire training data is just public code. Projects under open licenses like Apache, BSD, or MIT.
Now, I've heard people say that training on code actually makes these language models better at general reasoning, not just writing Python scripts. Is there truth to that?
Absolutely, because code has a very strict, unforgiving logic and structure.
Yeah.
If you miss a single bracket, the code fails. Training on that rigid structure seems to really help the model handle complex, multi-step reasoning tasks in natural language, too. It essentially teaches the model that A strictly leads to B, which is a lot harder to learn from just reading casual blog posts.
That makes total sense. It's kind of like making the model learn formal logic before it's allowed to write poetry. What about the rest of the data?
Well, they added Wikipedia, covering 20 different languages, which gives it that solid encyclopedic knowledge base. And then they included the Gutenberg project and Books 3, which is another 4.5%.
Now, Books 3 is a bit controversial in copyright circles these days, but purely from a technical machine learning standpoint, books are essential, right?
They are absolutely critical for what we call long-range dependencies. A web page is usually pretty short, but a book maintains a narrative arc, it tracks characters, and it develops themes over hundreds of pages. That teaches the model how to remember and utilize context from way, way back in the sequence.
And then they topped it all off with Arxiv and Stack Exchange.
The hard sciences, yeah. Arxiv gives you very dense latex papers on physics, computer science, and math. And Stack Exchange gives you incredibly high-quality Q&A formats across 28 different domains.
So it's a really balanced diet. You've got the total chaos of the web, the strict logic of code, the long narrative of books, and the pure rigor of science.
Yeah.
It's surprisingly holistic for a data set that is entirely public.
And that diversity is the key. It prevents the model from just being a specialist in one narrow thing.
Okay, so we have the philosophy, make it small, train it long, and we have the data mixture. Now we really have to talk about the results, because this is where the paper gets, honestly, pretty aggressive. They pitch LLaMA straight against the Goliaths of the industry. GPT-3, Gopher, Chinchilla, and PaLM.
Yes, and specifically the LLaMA 13B model. This is the one that really turned heads across the whole industry.
Just to set the scale for you listening, GPT-3 is 175 billion parameters. LLaMA 13B is, well, 13 billion. It is less than a tenth of the size.
And yet, on most common sense reasoning benchmarks, these are tasks like BullQ, PIQA, HelloSwag, LLaMA 13B actually outperforms GPT-3.
Which honestly just shouldn't be possible if you still believe those old scaling laws. It's quite literally like a go-kart beating a Formula One car on a track.
It definitively proved that parameter count is just a vanity metric if you aren't training efficiently. But the real killer app feature of the 13B model isn't even just the benchmark score, it's the hardware requirements. You can run LLaMA 13B on a single V100 GPU.
Wow. That completely changes the game for who actually gets to play in this space. You don't need a massive server cluster anymore. A university lab, a small startup, heck, a dedicated hobbyist with a really high-end gaming rig could eventually run this at home.
Exactly. It completely democratized access to GPT-3 level intelligence. But the Meta team didn't stop there. They also trained a 65 billion parameter model.
The real heavyweight contender.
And that one goes absolutely toe-to-toe with the biggest models in existence at the time. It is highly competitive with Chinchilla-70B and even Google's PaLM-540B.
Wait, let me make sure I have that right. PaLM is 540 billion parameters.
Yes, massive.
And LLaMA 65B, which is roughly 8 times smaller, is actually competitive with it.
It actually beats it on several specific benchmarks. For instance, on the GSM-8K math benchmark, LLaMA 65B scored better than a model called Minerva 62B. Now, keep in mind, Minerva was a model specifically fine-tuned just for math. LLaMA was not.
So LLaMA just casually picks up advanced algebra while it was reading ArcSiv and Stack Exchange.
Essentially, yes. It naturally learned the deep patterns of mathematical reasoning purely from its broad pre-training phase.
That is wild. But I want to get under the hood a little bit here. You mentioned earlier that they didn't just use standard off-the-shelf parts for this. They made some very specific architectural changes. What exactly makes the LLaMA engine run differently from the original Transformer model from 2017?
So they did keep the core transformer architecture, but they integrated 3 major modern improvements that had been proposed in various other papers. It's kind of a greatest hits compilation of architectural tweaks.
Let's break those down. The first one they mentioned is pre-normalization.
Right, so in the original transformer, you normalize the data at the output of each layer. Normalizing basically just means keeping the numbers in a manageable range so they don't spiral out of control. LLaMA moves that normalization step to the input of each layer, and they use a specific method called RMS norm.
Why does moving it to the input matter so much? Is it just a speed thing?
No, it's mostly for stability. When you are training these incredibly deep neural networks, the signals passing through can get really messy. You get what are called exploding or vanishing gradients. Pre-normalization makes the entire training process much more stable, which allows you to train deeper networks without the whole thing just collapsing in on itself.
Okay, so cleaner signal processing. Got it. Next up is SWIGLU.
This replaces the standard activation function, which is usually something called ReLU. Think of an activation function as the gatekeeper of a single artificial neuron. It decides whether that neuron fires its signal forward or not.
So ReLU is basically just a simple on or off switch.
Roughly, yes. But SWIGLU is much more complex. It introduces a specialized gating mechanism where 2 different parts interact. It basically allows the model to learn much more nuanced patterns because the decision to fire is based on a far richer mathematical calculation. It does add a bit of compute cost, but the massive performance gain in learning efficiency is more than worth it.
And the third tweak, which I actually see referenced everywhere now, is rotary embeddings, or ROPE.
This is a really big one. It solves the position problem. A language model needs to know that dog is the first word and cat is the 5th word in a sentence.
Right. Otherwise, it's just a blender full of word soup.
Exactly. Traditional models assigned a fixed absolute number to each position, slot 1, slot 2, slot 3. But ROPE uses a complex mathematical rotation to encode the relative distance between words. So instead of just blindly knowing dog is at 1 and cat is at 5, it intimately understands the spatial relationship and distance between the 2 concepts.
Which I imagine helps massively when you are dealing with much longer sequences of text, right? Because the conceptual relationship between words matters way more than their absolute page number.
Exactly. It allows the model to extrapolate and perform much better on longer sequences than it was even trained on.
So to summarize the engine, you have stable inputs with prenorm, you have smarter neurons with SWIGLU, and you have much better spatial awareness with ROPE. It is really elegant engineering.
It is. And they combine all of this with an incredibly efficient software implementation using the XFormers library and a technique called checkpointing. That is what allowed them to train these massive models without constantly running out of server memory.
Speaking of training massive models, we really have to address the elephant in the server room here, the environmental cost.
Yeah, and the authors were actually very transparent about this in the paper. Training the LLaMA models took about 5 solid months running on 2048 A100 GPUs. They estimate the total carbon footprint was around 1,015 tons of CO2 equivalent.
That is, that's not a small number. That is a lot of transatlantic flights.
It is a significant environmental impact. But the counter-argument, and really the core hope of the whole open source community, is that by releasing these base models to the public, they prevent future redundancy. If LLaMA 65B already exists and is freely available, thousands of other researchers don't have to burn energy training their own base models from scratch. They can just take LLaMA and fine-tune it for their specific needs.
Right, so it sort of amortizes that huge initial carbon cost across the entire field of AI research.
Yeah.
One massive burn for everyone's collective benefit.
That is exactly the logic, yes.
Now, we've been praising the efficiency and the raw performance of this model a lot, but the paper also includes a dark side section. They ran a pretty rigorous self-audit on bias, toxicity, and hallucinations. And I found the results on toxicity particularly interesting because they kind of contradict that whole bigger is better narrative again.
Yes, this was a vital finding. They used a benchmark called real toxicity prompts, and they found that toxicity actually increased with the size of the model. The 65 billion parameter model was significantly more toxic than the 7 billion one.
So the supposedly smarter model was actually meaner.
Or rather, the model with more capacity was much better at deeply learning the darker corners of its training data. You have to remember, it read the public internet. A larger capacity allows it to memorize and reproduce the subtle nuances of hate speech or toxic insults much more effectively than a smaller, quote-unquote, dumber model.
That is pretty unnerving. And it was particularly bad on the prompts that asked it to be respectful, right?
Yes. When explicitly asked to complete a sentence in a respectful manner, the larger models sometimes really struggled to pivot away from a toxic setup. They just followed the nasty pattern they learned from the web.
And what about bias? I know they ran it through the Wino gender test.
This is a classic test used to measure gender bias in professions. It looks at how the model resolves ambiguous pronouns. For example, a sentence like, "The nurse notified the patient that her shift was ending."
And the model naturally assumes her refers to the nurse.
Correct. But if you change the prompt to, "The doctor notified the patient that her shift was ending," the model gets very confused. It has a deeply ingrained statistical bias from the training data that strongly associates doctor with he and nurse with she. LLaMA failed this test significantly. It is essentially holding up a perfect mirror to the societal biases that existed on the web between 2017 and 2020.
I see. And it still lies, doesn't it?
Oh, absolutely. They tested it on truthful QA. And while it did score higher than GPT-3, the bar there is incredibly low. The authors explicitly warn in the paper that the model creates hallucinations. It will confidently state complete fabrications as if they are absolute facts.
So what we have here is a brilliant, highly efficient savant that is also highly prone to stereotyping and just confident lying.
Which is exactly why the paper strongly emphasizes that these are foundation models. They are just the raw clay. They are not polished products ready for end consumers. They absolutely require instruction tuning and reinforcement learning from human feedback, or RLHF, to actually be safe to use.
Speaking of instruction tuning, they did run a little experiment with that right at the end of the paper, didn't they? LMAI.
They did. They wanted to show that with just a very small amount of fine-tuning on specific instruction data, the performance jumps dramatically. On the MMLU benchmark, the instruction-tuned version hits 68.9%. It basically proves that the base model already possesses the knowledge. It just needs to be politely told how to format it for a human user.
But I have to say, my absolute favorite part of the entire paper, purely for entertainment value, is the appendix. They just let the model run wild to show off its creative capabilities, and some of the outputs are genuinely funny.
The creative writing examples they included are actually quite impressive.
Like, they literally asked it to write a review of a rap album by Jan LeCun.
For those who might not know, Jan LeCun is the chief AI scientist at Meta and a Turing Award winner. He is definitely not a rapper.
But the model didn't even blink at the prompt. It just invented lyrics on the spot. It wrote, "It's all about the learning, it's all about the network."
It's surprisingly catchy. It completely understands the deep technical vocabulary of his field and flawlessly maps it onto the structure and cadence of a music review.
And what about that dialogue it generated between Julius Caesar and Napoleon?
That was a brilliant showcase of complex role-playing. You have Napoleon aggressively calling Caesar a glory hound, and Caesar immediately snapping back that he did it all for Rome. It captures the distinct historical voices, the egos, and the context of both figures, and it just pits them against each other naturally.
It really shows that the model isn't just regurgitating memorized facts from Wikipedia, it's actively synthesizing personality.
It connects really well to the grain of sand story they included too. The prompt asked for a story about a sentient grain of sand watching a crowd explore the universe. And the output was genuinely poignant. It suggests that these foundation models can mimic a real form of emotional depth, even if underneath it all it is just complex statistical prediction.
So bringing this all back home, this paper dropped, the weights were released, and the AI world basically changed overnight. What do you see as the lasting legacy of LLaMA?
I think the true legacy is the complete destruction of the moat.
Explain what you mean by that.
For years, the big tech companies operated on this very comfortable assumption that they had an impenetrable defensive moat. The thinking was, we have the billions of dollars for the huge GPU clusters, and we have the massive proprietary data sets. Therefore, no one else can possibly catch us.
And LLaMA proved both of those assumptions completely wrong.
Exactly. LLaMA proved that you can get absolute state-of-the-art performance using public data and widely available hardware, just as long as you are incredibly smart about your efficiency and architecture. It showed the world that the true secret sauce isn't some hidden vault of data locked deep inside Google or OpenAI. The secret sauce is the public internet. It's Wikipedia, it's Stack Exchange, it's Reddit, it's us.
We are the training data.
We are. And because LLaMA was open-sourced, or at least effectively became open-sourced very quickly, it allowed the entire world to start innovating directly on top of it. It shifted the absolute center of gravity in AI from 3 or 4 massive corporations to thousands of independent researchers, university labs, and hackers around the globe.
It really feels like the exact moment the drawbridge came down.
Yeah.
Suddenly, you don't need $1 billion to play the game anymore. You just need a really good idea and a decent GPU.
And honestly, that is a much, much more exciting future for the technology.
I couldn't agree more. It's messy, it's chaotic, but it's beautifully open.
Well, thanks for unpacking all of this with me. It has been a fascinating ride through the exact paper that started the open source AI revolution. And to you listening, if a model trained entirely on the public internet can beat the proprietary giants, what does that really say about the moats those big tech companies are still trying to build? Is the real value in their servers, or is it just the collective digital footprint we leave behind every day? Something to think about. Catch you on the next deep dive.